Howdy, everybody. We're going to start talking about section 7.2, which is on properties of parallelograms. So a parallelogram is going to be one of the major kinds of shapes that we're going to take a look at in chapter 7. It's a four-sided shape. Four-sided shapes are called quadrilaterals. The other very important thing about a parallelogram, something that we're going to know is true right off the bat, is that it's going to have two sets of parallel sides. And so hopefully you're coming to this lesson with that kind of information. And then what we're going to do today is we're going to add some pieces onto that. So the first thing that we have right here is we've got a couple of theorems. And so we're going to use these to kind of add some extra information about parallelograms that you might not have known before today. So our first one right here is called the parallelogram's opposite sides theorem. And basically this is one is going to say that not only are these sides that we have in our parallelogram, are they going to be parallel to each other? So we've got a parallel set on the top and on the bottom. We've also got another set of parallel sides on the right and on the left, but we're also going to make the statement that these sets of sides are also going to be the same length. So we have these matching sets of tick marks on the top and on the bottom, and we have another set of matching tick marks on the left side and on the right side as well. So that's double that we had before. Parallelogram opposite angles theorem. So now the same kind of thing is going to happen here. We have our parallel sides, which are going to exist on the top and on the bottom, on the left side and on the right side. And what we're going to do this time is we're going to add on some angles. I noticed that I have a set of larger angles, which I might call obtuse, and I have a set of smaller angles that I might call acute, and both of those sets are going to match up nicely. So our obtuse angles are going to be matched set that are going to reach across the triangle from each other. And we also have a set of smaller acute angles, and they're going to have a match set as well. And once again, you're reaching across the parallelogram from each other. Next one is going to be the parallelogram's consecutive angles theorem. So now with this one, what we're talking about here is, once again, we're starting off with our two sets of parallel sides. And instead of talking about the angles that are match set, which you can see, we have y here and a y here, and you have an x here and an x here, but rather what we're going to do is we're going to talk about an angle and matching it up with the consecutive angle, which means that's the angle right next door to it. So we're going to reach up to this guy right here. Not the same, not the same. So we have one that's labeled as y degrees and the other one that's labeled as x degrees, and that's okay. In fact, if you take a look right here, we don't use the word congruent this time. What we use instead is the word supplementary. And basically what this means when you say the word supplementary, it means that these angles are going to sum up to 180 degrees. So another way to say that is that if you have that y degrees that we were talking about earlier, and you add to it x degrees, then what you're going to end up with is 180 degrees. So that's going to work out that way right there. Now it also works in this direction right here. You don't have to pair them up on just the left side. You could pick the two values on the bottom, because once again, you have another x degree angle right over here. So you could pick those guys up as well. And similarly up here, you could take the top two, or you could take the ones on the right, or the bottom two, or the ones on the left, whatever sets you'd like. And our last set. Our last set right here is not going to seem very important today. It's probably the one that we'll use the least today, but when we meet again to talk about section 7.4, we're going to use this one a bunch. And so this one's the parallelogram's diagonals theorem. So if you take a look right here, what I'm doing is I'm starting off with my shape that's got my parallel sides on the left and on the right, on the top and on the bottom. And what I'm going to add is I'm going to add in some of these diagonals that are going to crisscross each other. Now, when I'm drawing that, I definitely drew a longer diagonal and I drew a shorter diagonal. So the diagonals themselves don't match. But what does match is that the distances on either side of this intersection point M right here, that matches. And the same thing's going to happen here with my longer diagonal. These distances on either side of that intersection point M are going to match again. And the word that we use to kind of describe this is the word bisector. Each diagonal is going to cut the other diagonal perfectly in half. It's going to bisect the other diagonal. All right, let's try out some problems and see if we can apply some of these theorems. So we're going to talk about what we're going to do with them. And I also want to make sure I'm talking about referring back to each theorem so we know the reason why we did what we did. So for our first example right here, it's going to ask us to find a couple of variables. And I want you to notice that you've got your x variable, which is going to be right over here. And then you've also got your y variable, which is going to be right down here. Now there's two variables, so we're going to need to do 2 times the work. So I'm going to have some work right over here for my x's, and I'm going to have some work over here for my y's. Now, x is right here. If you take a look at x, this is information that's outside the parallelogram, and that means that it's side lengths. So when we're taking a look at our x piece of information right here, we want to compare it with some more side lengths. And so if I look on the other sides, hopefully I can find some more information. That's where the 13 is going to come into play right here. That's another side length. These side lengths are opposites, so that means they're equivalent. Now I should be able to solve pretty quickly and easily for x. I'm going to subtract the 6 from both sides so I can get my x variable alone. And when I do that, I will get my x value, which is going to be 7. Y. Y, if you take a look, is inside the triangle, which means it's not a side length, it's an angle measure. I don't want to use any side length information like 13 or the x plus 6 in order to find Y. That's different kinds of info. So what I do want to do is I want to find some other angle measures. When I'm working on my angle measure Y, I notice I have my 68, and the relationship here is not that they're next to each other, but rather that they're opposites of each other. You have to reach all the way across the parallelogram to get from one to the other. And because they're opposites of each other, that usually means they're congruent. So for Y, it's pretty easy. To get Y, all you got to do is just basically copy and paste what your other opposite angle is going to be. You try problem is going to go pretty much the same. See if you can pause the video and try that one out on your own. For our x value, we're going to do our similar kind of setup where we're going to compare our two side lengths to each other. And then you can get your x value. For our y value, we're going to do the same kind of thing we did before with our opposite angle. Both the y angle and this 123 are both obtuse angles, so they should be a matched set. For the z angle, however, z is going to be a little bit different. For z right here, you'll notice that it's not opposite the 123, but it's rather consecutive to it or right next to it. And so that means that what's going to happen here is with z and the 123 combined together should give us 180. So we should be able to solve that right there. You can do a little bit of subtracting that 123 from both sides. And when you do your subtraction from both sides, that will give you your z value. Our z value is going to be a small angle because it looks like it's acute. And I get the number 57, and so I feel good about that. So we're going to get a couple of different techniques right there that we're going to use. When we were comparing the side lengths, we were using the opposite sides theorem, reaching across that parallelogram to find those opposite sides. When we were using our y variable, which is our angle measure, we were using the opposite angles theorem. We were reaching across that parallelogram to find those opposite angles. And when we found z, we were using the consecutive angles theorem because we had used a z that was right next to the 123, not opposite the 123. All right, on the back side right here, we've got some more important examples that are a little bit more abstract. If you take a look, we've got another parallelogram right here, and we've got a couple of vertices with T and O and V. There is a fourth vertice, which is U right over here, and if you notice, it's blank. So we need to see if we can figure out what the ordered pair is for this guy right over here. Another thing to notice is that if you take a look at T and V, you'll notice that they're not numbers in there, but rather there's letters, M and K and H. And O right here, it does have numbers, but it happens to be a not very helpful number. It's 0, 0. So let's talk about T for a couple seconds. T is located at M, K, which means if you want to travel to that point right there, what you need to do is you need to travel over M units, and then you need to travel up K units. And when you travel over M units and up K units, you end up at this vertex right here, which is going to be T. Now I need to do the same kind of work right here for U. I need to figure out exactly how far over do I need to travel and how far up do I need to travel in order to get to that U value right there. And so I'm going to see if I can figure that out. Okay, so now to begin with, let's do the horizontal piece. How far over? That's going to be my X value or my first number in my blank right here. To travel over that distance, it's pretty far. And so I'm going to start, if I can see if I can chunk it up a little bit. First distance that I know pretty well is this distance right down here. That distance is the distance from point O to point V, and it's a horizontal distance. That's going to cover most of the distance that I want, but not all of it. How far is this distance that I'm talking about right here? Well, if we take a look at point V, it has an X value of H. So we moved from a point that had an X value of 0 to an X value of H. This distance that I've kind of marked off here in green has a length of H. Now that's pretty good, but once again, there is some missing right here. I also need this portion right here. That would be very, very helpful as well. Now I don't have that right now, and I don't have any points out here that would be able to kind of help me out with that one. So I am feeling a bit lost at the moment. So I'm going to need to look in a different place in order to kind of get this information. The distance that I'm looking for right here can be found, but it's not down here where I want it to be. It's located in a different spot. Specifically, it's one that we've actually already talked about. This distance right here is going to match with this distance right here. And you can kind of see that very clearly. This triangle that we have right here is going to match with this triangle that we have right here. Both of them are 90-degree triangles. Both of them have these congruent opposite sides. And both of them are going to have these exterior angles that are going to be congruent as well. So there's a whole bunch of pieces that are going to point to these pieces being the same. And you can see that right here as well. We had talked about that distance already. That is a distance of m. And so over here, it gets to be a distance of m as well. So how do I get from this point O all the way over here to where we need to be under U? Well, I needed to travel the distance of h and the distance of m. So this is going to be called h plus m. That's a bit abstract. There's no numbers there. We didn't come up with a new variable. We just used what we had and we put them together in the best way we could. I want you to notice that for all of this information, we used x values here and x values here. We didn't use any y values because we weren't looking for a y value. For our second value that we have right here, this one's going to be a y value, and we're going to look for that one next. For this one, we want to see if we can find some more y values to look at. I noticed that most of my y values right down here are going to be zeros. That's good to start from, but it's not going to be my final answer. I also noticed that this point right up here is going to have a y value of k. Now, the great news is that this point up here is actually even. This is a horizontal line, and so both of these points should share the same y value. And so if we have a y value of k right here, that is going to work out just fine. That one doesn't need any adding or at all. It is the height that it is. There's nothing extra to add on there, so we're good to go. All right, you've got another problem right here that is your you try it problem. See if you can try that one out. First piece right here is referring to that word regular. I call this one a regular polygon, but I bet you wouldn't call it a regular polygon. I bet you would call it a square. Now, why would you call it a square? Squares are kind of special, and you can see that square shape right here. And one of the things that makes squares special is that they have congruent angles. 4 congruent angles. That angle measure is 90 degrees here, but that's neither here nor there. That's not what I'm looking for. I'm just going to keep it general by saying that they're congruent angles. Another thing that makes a square very important is that it has 4 congruent side lengths as well. When you hear that word regular in the future, this is what I want you to think about. And this can be used for other shapes as well. So you can have a regular triangle, like this guy right here, which we usually call an equilateral triangle, that has 3 congruent sides and 3 congruent angles. You can even have other shapes, like you can have a regular octagon, and that would have 8 congruent sides and 8 congruent angles. As long as the side lengths are congruent and the angle measures are congruent, that makes it a regular shape. Next one, what about the missing pieces, S and T? So S and T are going to be 2 locations, and they're both going to need some ordered pairs, so we're going to see if we can find those. Once again, when you're looking for the x values, focus on x's. So for S right here, in order to get from this y-axis over there, how far do you need to travel? Well, the great news is, since we know it's a square, I know that all of the side lengths are the same. So if this side length right here, if I could figure out this one, I could use it in a lot of other places, and so I plan to. The distance right here is important to me because I'm starting with 2 points that I know. There's no mystery like there is over here. So I know that I'm starting here at 0, 0, and I'm going to go to 0, A. And since the y values right here are changing from 0 to A, I know that the distance I'm going to travel right there is A. Now it's going to be true down here and over here as well. So how do I get from over here to, from this point at the origin over here to T? Well, I need to travel over a distance of A. And the same thing is true for S. I need to travel over that same distance of A in order to get underneath that S point. Okay, vertical component. What about the vertical component? For T, you don't have to travel over, vertically at all. To get from the origin over to T, you just travel to the side and you don't move up and down. So that is just going to have a 0 right there. For the S, on the other hand, you do need to travel up and down. And I've already labeled it. I know that I need to travel vertically a value of A. So that one's going to go in there as well. Let's take a look at the same type of problem with another missing ordered pair, but this time I'm going to give you numbers. So if you take a look right here, we've got a couple of ordered pairs. So let's see if we can plug them in. W is going to be at -1, -3. X is going to be at -3, +2. And Z is going to be at 4, -4. Okay, so now this shape is supposed to be a parallelogram, which means that if I could have these points connected, I should get that normal parallelogram shape. Now I'm missing a point. There needs to be another point in here, and then that point is going to create our parallelogram. One of the first things I want you to try to do when you're working on a problem like this is I want you to just kind of ballpark where you think the point could be. It could either be in the upper right-hand corner, in the upper left-hand corner, lower left-hand corner, or lower right-hand corner. Hopefully you have a good guess. My gut tells me that it needs to be in this upper right-hand corner, so I can bring another line up here and then another line kind of across here and get that parallelogram shape. And so I'm banking on an answer that's going to be over here. Now, the next big question, though, is how do I get the exact value? There's a whole bunch of tools that you can use, but a really, really good one is slope. Slope is really, really fantastic because it's quick and easy, and there's a whole bunch of different ways that you can think about slope. Here are a couple of things that work great for slope. One of the things that I love about slope is you can just think about it simply as rise over run. Another thing that you have is you have a formula for slope that is y2 over minus y1 over x2 minus x1, and you can actually calculate slope. Rise over run is something that we can use on the graph. This formula is something that we can calculate using our numbers right here. Something I don't need you to think about is this. Most of the time when I mention the word slope, this is the first thing that comes to students' minds. It's got slope in it, that's for sure, but it's also got a lot of other things in there, and we really don't need those. So if I'm only talking to you about slope, then we want to really kind of focus on slope. So thank you so much for remembering about slope-intercept form, but that's not really what we're here for today. Okay, let's see if we can use slope. Here's what I want to do. What I want to do is, I know that parallel lines have the same slope, and so I want to see if I can build myself a parallel line to a line that I already have, which is this line right here, which you call xw or wx. If I wanted to know the slope of this line, and I'm thinking about it as rise over run, I can just do a little bit of rising, 2, 3, 4, 5. And I can do a little bit of running, 2. I ran to the left there, so I'm going to make it negative. And I know that there should be another line very similar to it right over here, and it should have the same slope because it should be parallel. So I'm going to recopy that same slope, 1, 2, 3, 4, 5. And I'm going to jump back to the left 2 units. And that should give me another point. If I add in my other lines that I should use connecting this point right here, I should just be kind of able to tell, do my lines look like they're actually parallel to my original 2 lines, or are they different? I'm feeling like they're looking pretty good, so I think that that's probably going to be point Y right there. So my Y value, let's see if we can come up with the perfect location for Y. It's that dot right there, and it looks like it's about 2 units over and 1 unit up. Next example is similar to that, except this time it says that the diagonals of the parallelogram, so we are bringing in our diagonals now, and they're going to meet at point Z right here in the middle. Find the coordinate of Z. So since we're looking at coordinates, it would be wise to know some of these other coordinates, so I'm actually going to take care of that right off the bat. V right here is an easy one to start with because it's at the origin, or 0, 0. Y looks like it's horizontally 1, 2, 3, 4, 5 units over, but 0 units up. X is the one that is farthest out. It looks like it's about 7 units over, and 1, 2, 3, 4, 5, 6 units up. And W right here is only 2 units over, and that one's also going to be 6 units up. All right, so now the Z point right here, Z is going to be smack dab in the middle. In our theorem about diagonals, we found out that diagonals bisect each other, which means that creates these equivalent distances on either side of them. So if we are traveling along one of our diagonals, this Z is the halfway point of that diagonal. It has the same amount of distance below the Z as it does above the Z. Now, you can look at either one of these diagonals. We have plenty of information floating around in our picture, but you are going to want to try to focus on just one of them, and then you can find the midpoint for that. I'm going to choose this one, Vx. One of the major reasons why I'm going to pick Vx is because this point V is so easy to work with. 0, 0 is great. Now, as I was talking about earlier, this is the bisector point, but it's also the midpoint. We have a midpoint formula, and that works out really, really great. Our midpoint formula looks like this. What you're going to do is you're going to take some x values and you're going to add them and divide by 2. And you're also going to take some y values and you're going to add those and divide by 2 as well. This is taking the average of the x's and the average of the y's. Like I said earlier, I was really excited to use this point right here because it's a bunch of zeros. So when I combine it with my other x value and when I combine it with my other y value, it's super easy to work with because I already know what 7 plus 0 is and 6 plus 0 right off the top of my head. This is going to work out really nicely, and I can type a couple things into my calculator, and we'll get the location of that point super quickly. 7 divided by 2 is 3.5, and 6 divided by 2 is 3. What do you think? Does it look like this point that we had right here was 3.5 units over and 3 units up? Let's find out. So I'm going to travel over 1, 2, 3, and a little bit more, and then I'm going to travel up 1, 2, 3. Yep, I think I hit it right on the head. So that's going to be a good value right there. Last one is you try a problem. See if you can pause the video and try that one out on your own. We've got a distance right here of GM, which is going to be 9. So I'm going to add that into my drawing. And we want to see if we can find GJ. Now, GJ right here is a full diagonal, which means it's going to be doubled. It is 9 on the upper side and 9 on the lower side. So that means our GJ right here is going to be 9 plus 9, and it's going to be 18. Now, our other piece that we want is angle GFJ. Now, GFJ is a 3-letter name, which means we want to go from G to F to J. We're looking for this angle measure right here. It's big. So if we can find it, that would be great. So we've got a couple other angles that we're looking at right over here, and we're going to see if we can put those together to come up with the very best answer. Something I'm noticing right here is that I've got this 37-degree angle, and it doesn't have to just live there. 37 is probably going to exist in some other places around because we've got so many parallel sides. And so this 37 also exists right here. And so now if I want this full angle right here, that is just going to be the combination of the 100 and the 37 that I have. That is now going to be a 137-degree angle. Now, it's not the angle that I want. Mine is still sitting right over here. But what can I do with that? Well, I also know that consecutive angles right here are supplementary. So if I want this angle right over here, what I'm going to do is I'm going to take the 180, which is our magical supplementary number. I'm going to subtract the 137 from it, and that should give me my final answer. So 180 minus 137 is going to give us 43. The angle measure that I was looking at was supposed to be acute, less than 90 degrees, and I get an answer that is also less than 90 degrees, so I'm feeling satisfied. Okay, that's everything that you need to know for section 7.2.